In Lesson 3 of the Abstract Algebra series, I explained algebraic structures with two operations. Among them, the field structure is perhaps the most important one. It is encountered in many applications in mathematics and physical sciences. In this video, I will present an application of field theory to one of the most well-known problems which puzzled the most important mathematicians since it was first proposed by the Greeks, the Delian problem, named so since it has its origins in the island of Delos. Using abstract algebra, it will be shown that a solution under the given conditions is impossible. In doing so, my presentation will also serve as a very basic introduction to algebraic geometry. First, let's understand the Delian problem and its history. The problem shows up in Plato's Republic, which was written circa 380 BC. 3 centuries later, Theon of Smyrna refers to the story in one dialogue entitled Platonic, of which only fragments survive. And another 2 centuries later, Plutarch revisited and commented on the story as well. When the island of Delos was facing an internal political turmoil, which was severely escalating the relations among the Delian citizens, the people of Delos asked the oracle at Delphi for a solution to the political problems. The oracle responded that the island should double the volume of the altar of Apollo, which was a cube. Initially, the Delians thought that this meant to double the edge of the cube, but soon they discovered that this was incorrect. Not knowing how to double the volume, they send ambassadors to Plato's academy to ask Plato about the solution. Plato interpreted the oracle's response as Apollo's advice to the Delians to abandon their political fights and instead immerse themselves into the study of geometry. Plato gave the problem to Eudoxus, Archytas, and Menaechmus, who solved it, but to his dissatisfaction, not with the purity Greek theoretical geometry required. Besides them, many more mathematicians who followed tried to solve it. Among them Hippocrates, Nicomedes, Apollonius, Diocles, Heron, Pappus, and Descartes. Eutychius of Ascalon, circa 480 AD, informs us about 12 solutions given to the problem. Among all solutions, the most important is considered that of Archytas, which makes use of 3 solids: a cylinder, a cone, and a sphere. Mathematically, if x is the edge of the original cube and y is the edge of the large cube, the problem requires that y cubed is twice x cubed. Therefore, y is x multiplied by the cubic root of 2. In Greek theoretical geometry, the length y must be constructed from x with the help of a compass and a straight edge only. Any known solution is breaking this rule. Despite all efforts to find a proper solution, efforts that lasted more than 2,200 years, no mathematician was able to do so. In 1837, the French mathematician Pierre Wansel proved that the cubic root of 2 cannot be constructed with a compass and a straight edge only. Wansel, who died a little short of his 34th birthday due to overuse of caffeine and opium and excessive work, produced results for several ancient Greek geometry problems. Mathematicians had overlooked his contributions, and only after Florian Cajori published an article about him many years later, Wansel's name became known. Reproducing Wansel's result is the goal of this video. Towards this goal, let's quickly review some concepts which will be important in the proof. A group is a set G with a binary operation star defined in it, such that the operation is associative. It has a neutral element, and each element has an inverse element relative to the operation. A group is called abelian if the operation is also commutative. The notation G** indicates the set G without its neutral element. A field is a set F with 2 binary operations dot plus and dot times defined in it such that F endowed with dot plus is an abelian group. F** endowed with dot times is an abelian group, and the 2 operations are linked by the distributive property. For a field, the notation F** indicates the set F without the neutral element of the additive operation dot plus. If F is a field and K is a subset of F, which is also a field under the same operations, we say that K is a subfield of F, or F is an extension field of K. When there is no ambiguity of the meaning, we can simply say that F is an extension of K. Examples of fields are the sets of rational and real numbers endowed with the operations of addition and multiplication. Therefore, the rational numbers are a subfield of the real numbers. Seen it the reverse way, the real numbers are an extension of the rational numbers. Another field example which was discussed in Lesson 1 was the set F, which contains all numbers of the form p plus q times square root of 2, with p and q any rational numbers. More generally, let F be the set which contains all numbers of the form p plus q times square root of r, with p and q any rational numbers. Then, given two numbers alpha and beta in F, we define their sum and product to be exactly what would be if we were doing the computation in the set of real numbers. Then, it's a routine exercise to check that F endowed with the addition is an abelian group. Similarly, F asterisk endowed with the multiplication is an abelian group. The distributive property also holds. Hence, F is a field. Furthermore, F is an extension of the field of rational numbers and a subfield of the real numbers. In theoretical geometry, any result must be the outcome of a construction drawn with the help of a straightedge and a compass. The straightedge draws straight lines and the compass circles. Given two straight segments of length s and t, which are not necessarily distinct, with the help of the compass we can transfer them on a single straight line, and hence we can add them. Similarly, we can subtract them. Using the straightedge and compass, we can draw parallel lines which pass through given points. As a result, we can construct the two figures shown on screen. Thales' theorem states that the sides of an angle intersected by a series of parallel lines are divided by them into proportional parts. From this, we conclude that the lengths x and y are the product and ratio of s and t. However, we can do more. Using the straightedge and compass, we can draw perpendicular lines which pass through given points. As a result, we can construct the right triangle shown on screen. The altitude dropped from the vertex of the right triangle is the geometric mean between the two segments into which the foot of the altitude divides the hypotenuse. Therefore, we can construct lengths which are square roots of other lengths. Now the question is if there are any other metric relations between lengths which can be constructed. The answer is no. Here is an explanation why. In theoretical geometry, the construction of any figure is a sequence of the following 5 fundamental steps. 1. Drawing a line through 2 points. 2. Drawing a circle given its center and 1 point on its circumference. 3. Finding the point of intersection of 2 lines. 4. Finding the points of intersection of a line and a circle. 5. Finding the points of intersection of 2 circles. If we use analytic geometry, then the previous steps correspond to solving algebraic systems of equations which are either linear or quadratic. Therefore, any constructible lengths in theoretical geometry can be the result of addition, subtraction, multiplication, division, and square root of other lengths. No other, more sophisticated operation is possible. Now I will rewrite the constructible lengths as an algebraic structure. Let K be the set of the lengths of all straight segments that can be constructed by a straightedge and a compass. The zero length is automatically in K as it corresponds to a line segment for which the endpoints coincide. Arbitrarily, we select a length to be the unit length. We endow K with the addition of lengths. The subtraction of lengths is seen as addition of the opposite length. For the picky viewer, I should say that the word length is not the best choice, since in its common use it implies a positive number. However, do not let this distract you. In your mind, replace length with algebraic value. We also endow K with the multiplication of lengths. The division of lengths is seen as multiplication of the inverse length. Given everything that has been discussed so far, K endowed with the addition and multiplication of lengths is a field. Obviously, it is a subfield of the field of real numbers. It can be easily seen that, starting with the unit length, using addition and multiplication operations, we can easily construct all integer lengths and their ratios. As a result, K is at least as big as the set of rational numbers. However, we found out that square root lengths are constructible. Let R1 be a rational number, which is not an exact square of a rational number. Then the set F1 is a field of constructible lengths which contains Q. Therefore, it is an extension of Q. You may want to call the set F1 as the set of hyperrational numbers. Yet, we could do better than F1. We can build a set of hyperrational numbers. In F1, we select a number R2 which is not an exact square of a number in F1. Then the set F2 is a field of constructible lengths which contains F1. Therefore, it's an extension of F1. In F2, we can select a number R3 which is not an exact square of a number in F2, and we construct the set F3 which is an extension field of F2. Continuing the same way, we can construct a series of extension fields which, in the limit, give the field K of constructible lengths. By establishing this series of fields, we have converted the original geometric question of doubling the volume of the cube to an algebraic one. Does the cubic root of 2 belong in any of the sets of the chain? The answer to the last question is negative. We will prove this in 2 steps. First, we will prove that the cubic root of 2 is not a rational number. And then, we will prove that the cubic root of 2 cannot belong to any of the sets of hyperrational numbers. For the first step, the proof is a variant of the famous Pythagorean proof that the square root of 2 is not a rational number, which uses the method by contradiction. Let's assume that the cubic root of 2 can be written as a ratio, k over L, of 2 positive integers, where k and L are relative prime numbers. That is, they do not have any common factor. Then k cubed equal 2 times L cubed. So, the k cubed must be even. But the cube of an odd number is odd. Therefore, k must be even. In this case, L cubed equals 4 times k1 cubed. This equation states that L cubed is an even number. By the previous argument, L must be even. We have thus concluded that both k and L must be even and hence must have 2 as a common factor. This contradicts our assumption that k and L are relative prime numbers. As a result, our initial assumption that the cubic root of 2 is rational is wrong. We now move to step 2 to prove that the cubic root of 2 does not belong in any of the hyperrational extension fields either. This proof also uses the method by contradiction. Let's assume that the cubic root of 2 belongs to the field Fn, where the index n is the lowest possible. That is, the cubic root of 2 does not belong to the field f n minus 1. The cubic root of 2 satisfies the algebraic equation x cubed minus 2 equals 0. Since the cubic root of 2 belongs to Fn, it can be written in the form p plus q times square root of Rn for some p and q in f n minus 1. The coefficient q must necessarily be non-zero. Otherwise, the cubic root of 2 would belong to f n minus 1. Substituting this expression in the cubic equation, we find s plus t times square root of Rn equals 0, where s and t are functions of p and q. If t is not 0, then solving for the square root of Rn, we find that it is equal to minus s over t. But then, this would mean that square root of Rn is an element of f in minus 1, which is not true. Therefore, it must be that t equals 0. Then, s equals 0 too. Notice that if we replace q by minus q in the expressions of s and t, s remains the same and t becomes minus t. However, being 0, they remain 0. This means that the number p minus q times square root of Rn satisfies the same algebraic equation as the cubic root of 2. As a result, we have 2 real numbers whose cubes equal 2, but there is only 1 cubic root of 2 in the real numbers. Therefore, the 2 numbers must be equal. This requires that q equals 0, which contradicts our assumption that q cannot be 0. We have thus concluded that the cubic root of 2 cannot belong in any set of hyperrational numbers and hence cannot be constructible. If you have reached this point, not only you have understood why the Delian problem is not solvable with the conditions imposed by theoretical geometry, but you have also understood what the topic of algebraic geometry consists of. Although there are some easier books on algebraic geometry, The topic of algebraic geometry has the reputation of being excruciating, abstract, and difficult. Unfortunately, this is a case where the negative reputation does not result from misconceptions or erroneous and unfounded claims. Indeed, in its purest form, it is a difficult subject. When you attempt to read formal algebraic geometry, you will encounter lots of abstract algebra which, in many advanced books, is obscured by the use of the concepts known as schemes and spec. However, its foundations lay on simple principles. And if one starts with them, it becomes easy to understand algebraic algebra and slowly build a solid path towards the hardest concepts. In this short epilogue of my video, I will only present to you an idea that permeates modern mathematics. This idea is also popular in sciences, with physics the discipline where it finds the most profound applications. Say that you're given a problem in geometry. In fact, the geometry may not necessarily be Euclidean geometry. The problem may be very hard to be solved using geometric ideas. Therefore, you opt to rewrite it as a problem in algebra, and you solve it with algebraic methods that make the problem more accessible. Once you have the algebraic solution, you can translate it back to geometric concepts and voila, the solution to the original problem. This idea is not new. You have been using it since your early days in school. You have studied analytic geometry, either as a dedicated topic or within other math ideas you have been exposed to. Analytic geometry solves geometric problems using analysis. That is, using coordinates and calculus, exactly because pure geometric methods are much harder to master. And with the last comment, I have finished my presentation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.